All right, we're rolling. Does anybody have any questions? Everything's going so well, nobody has questions. Yes? Oh, I always make homework that I can't actually do myself to push you. Just kidding. Number 3. Let's see what it says here. Show how to generate the plot seen in figure 912 using LT Spice simulations. Lucas, do you have something to turn in? I'm growled out, man. It's funny the first or second, third time it's not so funny. All right. The 2 people that turned in homework last are both named Anthony. Too bad there's not a race with the bet on who's last. All right, 912. Let's do it. Let's go to 914. And I'm going to cheat. And I'm going to go here. And I'm going to go here. View, list, 9, 14. What do you think of the time of this class? It's okay? All right. Would you rather be like 7 a.m.? Oh, yeah, you would. You like Dr. Schill doing that early, don't you? Holy crap. All right, so this problem wants us to generate this plot with LT Spice. So the threshold voltage, what does the threshold voltage mean? The device starts to turn on and you get a little bit of current, right? Does everybody agree with that? All right, so here's how I'm going to do it. I think I could think of a lot of ways. I guess Anthony's not the last one. All right. This is what I'm going to do. I'm going to go get the scissors out. All right. And then I'm going to put a current source in here of a small value. Because I know a little bit of current flows, 100 nano. I've already forgotten. Who was the other person that came in late? Henry. All right. And then I'm going to take this source right here, and I'm going to move it. I'm going to call this source B source to bulk. Looking good? And I'm going to do it. I'll do this a couple ways because I don't want you to think I know magic. All right. Whoops. Did I not change that to V source to bulk? And let's see, that's what it's plotting, right? V source to bulk. Now I'm going to get the scissors out here. And I'm going to you know what I'm going to do to make it easier? Grab this, move this up, get the scissors out here, and I'm going to stretch that down. I'm going to grab this, Control R it. Guess that's good. Oh, I have the ground in the wrong place. Then I go boom. And I go. So next year, if somebody looks at the old lecture, they'll know how to do this problem. Do you think that's really fair? I think I should stop doing videos. Just saying. So what's the substrate for this NMOS always at? What's the substrate? Well, what terminal is the substrate? Body, right here. So one more time. What's the voltage of the substrate always at? Ground. Right? Okay, so now here's what I'm going to do. And we don't need all of this. And actually, why don't I, before I forget, save file, save as, go to my desktop, go to EE220, go, oh, thank you. They're all blending together. It's just a number. View, list. Those 221 students don't want me to teach 220 anymore. They told me to teach 320 in the fall. And then I asked them, I'm like, well, what about the 220 students? You know what their response was? Screw them. I'm like, really? Yeah. All right, lecture 5. That's what I told them. I'm like, no. Example 1. All right. And then here. And then let's grab the ground. Let's move this dude up. And then let's get the old scissors out. And then there we go. So I'm going to force a little bit of current through there. And I'm going to be fancy. Where's VGS? It's right here, right? So we'll see, I'm going to show you some fancy stuff here. So I'm going to get this little source here, Control E it, press G, change this to 1. Then I'm going to connect. Is anybody thinking, how the hell are we supposed to know to do this? I'll see if I can think of another way to do it that's different. All right.
I think I got it a decent way with figure 9.13.
All right, we'll try it. That'll be the next way we do it. VGS, everybody looking good? So why'd I use this? What's that? Well, it just makes so I can plot VGS directly. So when I do the plot, what am I going to plot for my x-axis? VSB. Let's do linear 0 to, how about, let's start at 0 and just go to, how about 2 volts and 1 millivolt steps. Looking good? We ready to run? Run. Let's make sure we plot this voltage and it should be a line. Looking good. Just VSB against itself. And then here I'm going to plot VGS. There it is. And let's make it so that it looks more like the figure. And how would I do that? 0. Just take the bottom and set it to 0. So just go boom, set the bottom to 0, set the top to 1.2, set the tick to, how about 200, hit OK. And I guess I could go just to 1, make it look a little better, I think. And then let's squinch it up. So at low voltages, it's saying that the value is about 0.64, and let's go up a little bit. And of course, you stupid thing. All right, and we'll just go 0, 200 milli. All right, you get the idea, right? Everybody see that the threshold voltage is going up with BSB? Does everybody understand why I can say that's the threshold voltage? All right, we ready to do, what was the other way?
If you use 9.12 or 9.13, it says that if the resistance is very high, then VGS will be about equal to VTH. So I just did that. I did it pretty much the same as you, except I didn't put that weird thing on the left.
Yep, sounds good.
Yeah, and then I just measured
Yep,
VGS and it was the same as that.
yep. Anybody else do it that way? All right, are we good with this one? All right, so let's continue with 9.5 AC. All right, so let's hit save and then hit yes. And then go over here, just make sure I save that. Okay, and go back here. And I want you to help me out. So let's sketch the circuit. If I remember, it looked like this, all 30 by 2 and 10 by 2. And you're going to help me remember the voltages from last time. And I'll draw this way. What was the name of this circuit? There's a whole chapter on this circuit, chapter 22, I think. Diff amp, differential amplifier. Okay, so help me label the currents. So, and the voltages, the DC values we calculated last time. What is that current? Oh, and this current? And this DC voltage? And this DC voltage? 2.5. And this voltage here? Isn't this 1 point something and this was 1.44? You know what? Let's utilize our notes. Does anybody ever actually use these? Are you sure? 1.44. They're spaghetti and they're hard to follow. Really? I don't think I should do it then, do you? You just take screenshots of the video and then print those out. All right, 1.44. And what was this voltage? All right, it was, we didn't solve for that, 3.842. And this voltage here, this voltage here, here's VSD 8.1. You know this is in the book too, right? So this voltage here is 4.9919. 4.9919. Any questions about that? We ready to do AC? And then what was the other thing we were going to do today? PMOS. Let's look at the homework and see if that would be a good idea. Homework that's due on Monday, February 10th. What do we have here? What device? The PMOS? These are PMOSs. It's PMOS diff amp. All right, so let's go back here and do the AC circuit. So tell me what to do. Oh, one other thing. Did we calculate our channel? Let's find out. Let's find GM. So what is tell me the easy way, you're doing your PhD qualifier, what's the easy way to find the GMN? It's to use the current, because you know 20 microamps are in each side. So that is, let me write it verbose first, which is also, where is this anyway? It's in the book, right? It's also and what is the KP for this process? Times what is it? Yeah, 20 micro. Let's see if I can simplify my life at all. This cancels. So that gives me 1200 times 20 or 24000. And if I did that right, that's microamps squared. So 2400 microamps squared is microamps. So 24000 shift square root 154. I've got the volts squared here. 154.9 microamps. So GMN equals roughly 150 microamps per volt. Anybody cool with that? Yes? That's volt squared. I was actually thinking about that. Because KP is microamps per volt squared, so you got microamps, volt. This is per volt. Looking good? All right. Let's see what today's quiz is on. PMOS. Ooh, you better pay attention to the PMOS. All right. You think I'm lying, don't you? Lucas. You think I'm lying, don't you, Lucas? What about the NMOS or the PMOS here? Without doing any math. What can I say and why? Yeah, it's the same. Why? KP is 3 times smaller, but the, yeah. So that's easy, right? And then the last thing I need to calculate is this R channel. Does anybody remember that equation? But here's where you'll make a mistake. Because this GM, we don't use it's in triode, we use KP sub P times W over L times VGS minus V threshold P, or VSG. But what is the place where you make the mistake here? Yeah, the VSG is what? What's the VSG here? 5 volts. Does everybody see that? So let's calculate our channel. (40 microamps times 30 over 2 times 4.1. If I leave it like that, is anybody going to look later and go, how did he get, oops, this is over 2, yeah. How did he get 4.1? And let's make sure you know. There we go, 5 minus 0.9. Let's plug and chug. So we get 40 E6 change sign times 15 times 4.1 equals shift 1x. Says our channel equals 406.5 ohms. Everybody looking good? We ready? AC circuit. Stop and cry. You're all AC gurus now from 320. All right, so I want to show you a trick before I do anything. If I have a MOSFET that's like this, what's this voltage AC-wise called? Don't all scream it at once. That's right, that's VGS. This is the gate, this is the source, this is VGS. Everybody follow that? What's the current that flows there called? ID. So what is VGS over ID equal to? No, this is in saturation. Our channel's for triode. Nope. What is, how do I relate ID to VGS? Everybody agree with that? So what is VGS over ID? So I can think of this for small signals as a resistor of 1 over GMN. Let's do it for PMOS, because I see Sony's looking confused back there. He's like, what the hell magic is that? All right, so I ask you again now, you're going to kill me. What is the voltage that I've drawn here? ESG. What is the current that flows? ID. That's equal to what? GMN times V, or P times VSG. And so this resistance, which is VSG, G I should be doing, all over ID equals 1 over GMP. So this is a resistor of 1 over GMP. So you should memorize that. Because when we do current mirror loads for diff amps in chapters 20, 22, etc., we're going to use that. We good to go? All right, so we know our parameters. So I'm going to redraw the circuit now to look like this. A resistor of, and let me see, 1 over GMP is, I already know the answer, but let's do it anyway, 6.5K. E6 change sign shift, 1 over GM is 6.66K. Everybody follow that? It's just 1 over GM. Any questions? Then I'm going to come down here, I'm going to draw my MOSFET, and at the gate I'm going to draw the AC. This is only the AC circuit. And I'm going to put this as 1 millivolt. I'm going to come over here, I'm going to draw my MOSFET. I'm going to put this gate at ground because that's AC ground. Now what do I do for my current source? How much current flows down there, AC current, through the tail current? None. Why? Why is no current flow through there? It's a DC. I can't change the AC current. So for AC, it's an open. Everybody see that? So I'm not going to draw that. Okay, but I am going to go up here and I'm going to draw my, what did I say, 406 ohms. Why did I draw VDD as ground? Well, because I can't change the AC voltage across the DC source, so it's ground. All right, so I'm going to ask you, we're going to go over this again when we do diff amps. All right, so I'm going to ask you simple questions. I'm going to do it for you. What's this voltage? 1 millivolt. What's the VGS here? I don't know, so I'm going to write it. Okay, so wait a sec. I want this to be clear. So if I have an AC going down through here, and let's just say it's 10 nanoamps, don't I need to have an AC current that's flowing up here by 10 nanoamps? Because if you say no, then where does the current flow? Does everybody agree with that? So here's the problem. When I was learning, like, well, wait, how can the current go down like this and go up like this? Current in an N-channel MOSFET flows from the drain to the source. Okay, so here's the thing. We draw the current like this, it means that the overall current AC plus DC is decreasing. So if there's 20 microamps here, this current goes from up to 20.01 microamps. This current goes to 19.99 microamps. So we say that AC is going backwards like this, or you could also say that the AC is minus 10 nanoamps like that. So the overall AC plus DC is decreasing, but we still draw the AC current as going back. Everybody got that? Because that was hard for me to learn. Because I'm like, how can the current go from the source to the drain? Current always flows down. It's not. You're just decreasing the overall current in that transistor. And here you're increasing, and I'll prove that more in a moment. So everybody see the deal? So if this is going down by 10, this is increasing by 10, this is decreasing by 10, the VGSs have to be equal and opposite. But I don't know that. I need to prove it. So let's do that. Let's write 1 millivolt equals VGS1. So I'm going here. And then this is in the other direction. Or how about I do it first time like I did it in circuits 1. So this would be 1 millivolt. I'm running uphill, 1 millivolt. Then I'm going downhill. So this would be minus VGS1. And then I'm going back uphill. And of course, these are tied together. Or VGS1 minus VGS2 equals 1 millivolt. Does anybody agree with that? Now, I can look and say that these have to be equal and opposite, so VGS1 would be half a millivolt, VGS2 would be minus half a millivolt, and they would sum to 1 millivolt, but I want to prove it. Okay, so I'm going to write ID1, ID2. So ID1 over GM N minus ID2 over GMN equals 1 millivolt. Or ID1 minus ID2 equals GMN times 1 millivolt. But these are equal and opposite, right? And so if that's the case, ID1 is equal to minus ID2. So that means 2 let's come up here, 2 ID1 equals GM times 1 millivolt, or ID1 equals GM times 1/2 millivolt. Now because of this, then GM, so this is VGS1, and then VGS2 equals minus 1/2 millivolt. I would bet, I don't remember, but I would bet the quiz today is on DC, some DC calculations. What do you think the quiz is going to be on Monday? AC. This is the hard part of the AC calculation. And I think this is open book. Open book and closed notes. Is that too nice? All right, so this is the hard part. I mean, you can look at it and say, oh, it's got to be VGS1 equals, but now I told you I would make sure you intuitively understand that. So let's make sure you do. So this source is, or this side's always at 0, AC ground, right? So let's say this side goes up. Doesn't that pull this gate up? If I've got a 1 millivolt source, won't that pull this gate up? All right, if it pulls it up, what does it do to this part? It pulls all of this up, but can it pull this up? Why? What is this? 0, but this goes up. So since they have the same currents, this will go up by 1/2 millivolt. This goes up by 1/2 millivolt, but what is VGS2? If this goes up by 1/2 millivolt, it's 0 minus 1/2 millivolt, or VGS2 equals minus 1/2 millivolt. Everybody see that? Now, when you do the sims, because I'm sure I assigned some homework on this, it's not going to be, I mean, if you put the MOSFETs in their own well, I mean, you connect the body to the source, it'll be precise. But because the bodies are at ground, there's going to be slightly different voltages because the VGS is left slightly different influence, but it'll be very close. All right, any questions on this? Okay, so I got a question. All right, if that's the case, actually, let me redraw the circuit so it's nice and neat. See, I wouldn't have to do this if it was PowerPoint. I could just sit there with you with the laser pointer and a clicker. On this slide, we see. All right. So this is 6.6K. And what did I just draw? No? What is the 6.6K? Which is from? What's this 406 ohm device? It's the PMOS in triode. What's this one? It's PMOS in saturation, where it's 1/GM. You need to, this will make life so much easier when you're doing problems. You don't need to go through with all the extra math. Oh, it's gate drain connected. If there's a current flowing through it, then it's a resistance of 1/GM. Okay, memorize that. Just like if it's gate drain connected, that means it's in saturation. Yeah. All right. So I go back now and I say, oh, I have plus minus 1/2 millivolt, plus minus 1/2 millivolt. This VGS is equal to 1/2 millivolt. This VGS is equal to minus. I'm going to pause right here. First question, does everybody see this is 1 millivolt and this is 1/2 plus 1/2? So I'm walking. Start walking. Go up by a millivolt, down by a millivolt, down by 1/2 millivolt, down by 1/2 millivolt. Does everybody see then if this is plus minus 1/2 millivolt that the VGS2 is minus 1/2 millivolt? So now, I write GMN equals 150 microamps per volt. What is the AC current that flows there? GM times VGS, or 1/2 millivolt, which gives me 75 nanoamps. It's the 150 micro times the 1/2 millivolt. Millivolt times micro gives me nano, and 1/2 times 150 gives me 75. Any questions? All right, what's this current then, without doing any math? Drawing down like this. Which means it's actually going up, which means the overall current is decreasing. So I would write this current, let's write it out, ID is equal to ID plus little id, which is 20 microamps minus 75 nanoamps, whatever, cosine of 2 pi f times t. This is the DC, this is the AC. Everybody good? Any questions? Because it took me a long time to figure out, oh, all that means is minus AC means it's decreasing. Overall AC plus DC is decreasing. So now, if this goes up a little bit, not as much, but turns this one on more and I get more current. But if this is at ground and this goes up, what does it do to this device? This is going up and this is at ground. What does it do to this device? Shuts it off a little bit. That's why it goes down. Okay, so let's continue. And let's write that this voltage is then what? Well, it's coming down like this. So it's minus 75 nanoamps times 66K. And if I wanted to write what that voltage is, AC-wise, it would, whatever that is, 6.6K times minus 75 nanoamps, which gives me a negative voltage. So if I look at this and I say negative voltage, I just went over this in circuits too. What does negative voltage mean? Means that it's out of phase with the input. So and I'm going to do the sum of this. When the input's going up, this terminal's going to be going down. It's out of phase. Any questions about that? And then if I look at this one, it's going to be what? What's the voltage? $75 nano, or minus 75 nano times 406. And that's just for the hell of, or it's in the book. You can tell me what the numbers are in the book. Are there any questions on this before I simulate it? Because it's being pulled from ground. So the current would be plus minus. Whoops. So the current is pulled this way. So current flows from plus to minus just like here. So if the ground is plus, then the output's minus, and I get a negative voltage out. Which means what? It's out of phase. I mean, it's not a big deal. It just means it's out of phase. And I want to go through this and make sure you follow. So let's look at let's look at 920. so here's our little circuit, and I'm gonna save this, or actually, I guess I don't need to. Let's just do a .op to begin with. All right, and I'm gonna hit run, and you know what the first thing I'm gonna do? I'm gonna check the GMs of these two transistors, because what did I calculate them to be? 150, and what I calculate this to be? 150, and I wanna see if that's right. So I'll go View, Spice Error Log, and let's look at M1 and M2. And I go over there, M1 and M2, GM. And they're all, see, this is what I was saying, they're not precise because of the body effect, but does everybody see that I calculated 150 and they're coming up with 142 and 144? All right, then the GM3 is 139 micro, and there's GM3. And then the M4 is a tiny little current, or a tiny transconductance, because it's in triode region. But what is of interest for M4? Remember, that's the one that's in triode. Our channel, how do I look at that? 1 over GDS. That's the conductance between the drain and the source, and this is roughly 2 milli. A little bit less than 2 milli. What's 1 over 2 milli? 500. So if I look and see, oh, what did I calculate? 406, right? So it's in the ballpark. Does everybody see that? Does everybody see how, before I waste a lot of time and chase my tail and try to figure out what's going on, I'm going to go look and see how the small signal parameters change, or how they are compared to my hand calculation. Looking good? Any questions? Okay, so now let's go do, or actually let's look first here. I said with body effect, we calculated at 1.44, but you see that it shows in the lower left it's 1.17. So what does that mean? There's a higher VGS. Why is that? We covered this last time. Body effect. All right, so the body effect makes it so the VGS is a little bit higher, but it's not that far off. Okay, now what about the currents here, the DC currents? What did I calculate? 20 on each side, but look, that's 19.88. And this one is 20.11. So why are they different? They obviously have the same DC VGSs, right? This terminal's physically tied to 2.5, and this one's tied to 2.5. Now, this is a really subtle question. If you get this on an interview, you'll impress people. Why is it they have slightly different currents? The body effect's exactly the same in each of those transistors. The sources are tied together and the bodies are tied together. What's that? It has to do with the BDSs, the drain to source voltages. Look at this one. This device is in triode, and it's pulling this almost, it was 4.99 volts, almost all the way to VDD. So that means this has a larger VDS. This one was at, the drain was at 3.88, so that means this one has a smaller VDS. So that means if I look at the current in this one, because even though the VGSs are exactly the same, and the body effect's exactly the same, because the VDS is bigger, if you look, it has more current, 20.11, than this one over here. So let me make sure you follow that. Does everybody agree this has a larger VDS? Okay, so if I go back and I look at this, I look here, I have, here's my ID versus VDS. Here I am. In one case, I'm right here, because they both have the same VGSs, so they have to land on this curve. So I have one right here, the one on the left, and the one on the right's out here at a larger VDS. So you can see this ID is, or this device is going to have a larger ID than this one. Now, this 1 micron process is pretty good because this is relatively flat. As you see, it's only off by like 0.4 microamps or something like that, whatever it is. The smaller devices can be worse. Okay, they can have much higher or much lower output resistance and more of a slope. Did everybody get that finer point? All right, are there any questions about, let's see, VD3 we calculate is 3.85, it's pretty close. This one we calculated is 4.99, and it is very 4.989. All right, everybody good? Any questions before we do the AC? So with the AC, I'm going to use the transient, and I put in 10 kilohertz, I guess, and let me change that to 1 kilohertz. Now remember, with transient, it's not like AC. With AC, I could put 1,000,000 volts here and it'll treat everything as small signal. With transient, I have to be careful not to go large signal. Because then my approximations are wrong. Okay, they start to get even more off than what we had before. So I'm gonna go over here now and do transient. And let's do, how about 3 milliseconds? And hit OK. Hit run, and let's do this first. So there's my input. So when the input goes up, what does VS12 do? Now it goes up. This whole thing goes up. The VGS will go down because this is AC ground. So let's go show that. If I plot that, notice it's in phase. So when the input goes up, VS12 goes up. Does everybody see that? So if I were to ask you, what is the AC, and you could use a current control or a voltage control voltage source, but what is the AC voltage of M1? Plot it. I mean, tell me how to plot the AC voltage of M1. AC voltage, I'm sorry, VGS of M1. Yeah, just go right here and I right click and I say minus VS of VS. Okay, now I'm going to pause here. Tell me, what am I going to see when I plot this? Big DC offset, which is about 1.1 volts or something like that. But I'll also see the AC because it's the only thing plotted. Does everybody follow that? So let's hit OK. And you see there is that AC. And it's going up when the input goes up, but it's hard for me to see it. So I'm going to then go over here and I'm going to put minus 1.3288. And what was it I calculated the VGS of M1 to be? 0.5 millivolt. But I said it's going to be off a little bit because the transistors aren't perfectly balanced. They have, for example, different VDSs. Okay, so what about the VGS of M2? So I don't know what this voltage is here. So it says node N001, so I'm going to go like this. V of N001. And you see how the VGS is out of phase? So the VGS would be minus 1/2. Well, it would be minus 0.4, but let's see. Now I'm going to subtract the DC offset, the 1.3288. And then you see, oh, you know what? Let me make this a little bigger. See that one of them's going to slightly above, looks like there's a slight phase shift too. 400, one's going to roughly 400. The other's going to roughly 600, but if I add them together, this minus this, does everybody see I get 1 millivolt? Okay, so now, Does everybody see that when this voltage goes up, this voltage goes up, this voltage does not change? So here I get a VGS that's positive when the input's going up, and here I get a VGS that's negative because this voltage goes up and this stays the same. Now what happens when the input goes down? When the input goes down, I get that the VGS of M1 goes down and the VGS of M2 goes up. Everybody follow that? So you see how they're out of phase? And then you say, oh, VGS1, the blue, is equal and opposite to VGS2. Any questions? You sure? Because guess what's going to happen on Monday? Quizzy. No, it's not on AC. I'm nice, man. All right, what's the next thing I'm going to look at? Real quickly, because I want to do the PMOS real quick. I'm going to look at this voltage here, which is 6.6K. So 6K times down is going to be micro. This, I'm going to guess, is a half a millivolt. So let's go back, hit save. Let's go to add plot plane. Go back over here and then show VD13. And then can anybody see that's half a millivolt? Yeah, probably, but let's make it clear so the grader doesn't get angry. Start screaming and talking to himself. Damn these students! Everybody see that? Oh wait, that's me. No, just kidding. Everybody follow this? Any questions on this one? And then the last one is this right here, which is 400 times 75 nano, which I'm guessing is 30 microvolts. No, 30 microvolts. I don't know. I think that's right. It's around 30. Let's go back. Add plot plane. Go over here. Hit boom. Go back. Subtract. Minus 4.98966. Boom. And I'm off a little bit. You can see the peak to peak's roughly 60, right? So why don't we get rid of yeah, that's what I'd guess too. Yeah, you get the idea. It's about, I guess, 30, just doing the math. Yes. Yeah, because it's on the other side. It's a good question. So the stuff over here, when this goes up, this goes down, and then you're saying this is going up because remember the current, oh, did I? Oh, yes, thank you. So this is actually minus that, so it'd be positive. Yes, you are right. Sorry, I missed that the first time. Looking good? We ready to do the PMOS DC? Are there any questions on this? All right, let's do the PMOS DC. So we have, I'm going to do this generic, all right? So I have a current source here, which I'm going to call I bias. And I come over here to an AC and a DC, and I'm going to call this V gate 3. This is M3. I'm going to come down here. And why don't I, yeah, let's just do the same old thing. Oops, I'm off a little bit there. So V gate 3, V gate 3. Then I'm going to come down. Let's be a little different this time. Find all the currents and voltages DC in this circuit. Tell me what to do. Quiz today. Well, let's do the easy part first. What are the gate voltages of the PMOS? So here I'm going to go BG3. Here I'm going to go BG3. Right? Now what? You got the same source voltage, same gate voltage, so what can I say? Anybody not follow that? What if one side was off? All that goes, then all of I bias goes through there. Okay? Now, how do I calculate this voltage? Yeah, I calculate VSG first, which is equal to what? 2 times I bias over 2, divide by Kp sub P times Wp over Lp, if we want to use that, plus V threshold P. So what is this voltage then? This voltage, what is it? I just calculated VSG. Yep, VG3 plus VSG. So this voltage is at VG3. This voltage is VSG. So this voltage is VG3 plus VSG. Anybody not follow? Sony. Now tell me how to calculate this voltage. No, NMOS. VGS equals the square root of 2 I bias over 2 times Kp sub n times Wn over Ln plus 0.8. Do I need to add anything to that? No, that's directly VGS. That's this voltage. Looking good? Okay, now how do I calculate this voltage right here? Ohm's law. I bias over 2 times R. What? All right, any questions on this one? I want to do one more thing before I quiz you. It's too early for the quiz. What's the thing I want to do? Rock and roll all night and party every day? You don't know any other song by Kiss than that one? What about Beth? I didn't know Kiss sang that song. All right. I remember when Kiss was popular in like 76 or so, and I'm like, I'm not getting it. I don't see what the big deal is. Okay, let's do the AC circuit. Incidentally, you know what else 1976 was besides the bicentennial? Oh, Vietnam was over by, I mean, totally over in 75. I think that's its edition when it officially ended, but it started winding down in like 72. 76 is when Saturday Night Live started. That's how long that damn show's been on the air. All right, AC circuit. So here I'm going to write V in, because we'll get ahead of next quiz. Do I need to write the current source? Whoops. on the top? No. Do I need to write the DC sources? No. Would it be okay if I wrote this gate drain connected device here as a resistor? And what is it? 1 over GMN, right? And then here, is it okay if I write it a resistor? Yeah, because it is a resistor. Boom. Okay, so now, here I'm going to write the voltages, plus, minus, plus, minus. And before we get going, intuitively, if this node goes up, what's going to happen to this transistor? Is it going to turn on or off? Off. Why? Because the gate's going up. It's a complementary. It's CMOS. It goes up. And if this goes up, what happens to this node? When I'm pushing, if I'm pushing a box, the box may contract as I push it, but what's on the other side of the box will also get the push, right? So if I push this up, this node's going up, this will go up less, this will compress, but this going up with this fix will cause this to go up. So if I write this, this will be VSG. This goes up, this goes down. Let's call this VSG3, VSG4, and this goes up. You know what else was really popular in 1976, which will make you laugh? Pong. Does everybody know what Pong is? Video game? I don't think, maybe it was the first, I don't know. Atari. All right. Tell me how to prove that VSG3 is equal to minus VSG4. From circuits 1. Here I'm going to write. So this says that because ID of 3 is equal and opposite to ID 4, that these two are equal, that VGS4 is equal to minus VGS3. Note that if VGS3 is minus 1 millivolt or half a millivolt, then minus means VGS4 is plus 1/2 millivolt. Does everybody see that? So it doesn't matter. I can put the minus sign over here. I could also write VGS3. Don't get confused on that. Look at this and go, hey, I'm pushing this way, which will cause this VGS3 to go down, which causes the current in this device to, this goes up. What happens to the overall current in this device? Goes down. I'm putting the gate, I'm moving the gate up and moving VGS3 down, so that shuts this off. And then if I do that, this node goes up. What does it do to the current in this device? Goes up. So make sure you follow this, because I can guarantee we'll have I love this problem because it goes over AC, DC, making sure you understand what's going on. So very likely we'll have it on a quiz, some variation like today, the DC part, and then on the midterm and maybe even the final. Any questions before we get ready to feel alive with the quiz? I guarantee you'll feel more alive after taking the quiz than you do at the end of the lecture. All right, no questions? Therefore, let's quit.